and q dv integral over b of t is the total q that exists in the deformed configuration. I want to know its rate of change. Okay. Now, those of you who know Leibniz rule would immediately say that, oh, you cannot just bring this time derivative inside, because the shape of this blob would be changing. So, the domain of the integration is changing in time. So, you cannot just bring this derivative inside. Okay. So, in a way, Reynolds transport theorem is actually a three-dimensional version of Leibniz rule that you guys know. Okay. What we are going to do now is actually the three-dimensional version of Leibniz rule. So, the way we are going to change this is, so any idea how are we going to do the change? How are we going to carry over with this derivation? What is the simplification that we can do? So, if I could get, instead of integral limits bt, if I could get b naught somehow, then I could bring the derivative inside the integral, right, which means if I could change this integral somehow to dv naught, then I could bring the derivative inside the integral. So, basically I am going to write this as d by dt b naught q x t times j times dv naught. Okay. I have written delta j I, yeah. No, capital J is summed over, no, here it is. So, if you want to write a matrix multiplication, let us say A inverse equals identity. If you want to denote this in index notation, you are going to have an inner index that is summed over, right. So, you are going to write this as A I k, and let us say A inverse is some matrix that is B k j, that is going to be delta I j, right. So, I have written this here. Okay. So, capital J is summed over. So, this is what we get. Now, we can bring the derivative inside, and what I get is that b naught d by dt of q x comma t j times dv naught, and we know all the quantities that appear in this time derivative. One important point is this is d by dt. Okay, I am looking at the rate of change of this quantity, neither keeping small x fixed, neither keeping t is fixed, nothing is fixed here. So, x is also a function of time, do not forget that x is a function of time. So, what we are going to get here is simply b naught. So, we are going to get the material derivative of q times j plus q times dj by dt, which is essentially del j by del t, keeping capital X constant. Okay. Capital X is always constant for us. This is what we get when I take that derivative inside. And now applying the material derivative here, what do I get? This is del q by del t plus u dot grad of q times j plus, what is del j by del t? Del j by del t is j times del dot u, this times dv naught. Okay, I'll write there. And now taking these two together, what are we going to get? What do we get? U dot grad q times j plus u dot del q times j plus q j del dot u. What do we get? Del dot of q times u, outside bracket j. So, we have del q by del t plus del dot of q times u, outside bracket j, dv naught. Changing the coordinates again, we get okay. So, through this change of variables, we brought the derivative inside, and just following and collecting all of our results so far, we get that the time rate of change of this quantity should be actually equal to, this was not planned or scripted, okay, it just happens that they came down in the same line. But yeah, so the time rate of change of q dv bt is actually equal to this term. The integrand can be modified like this, and this is the definition of Reynolds transport theorem. Okay, this is the definition of Reynolds transport theorem. And the good thing about deriving my Reynolds transport theorem this way is that now you can straight ahead visualize and apply all the laws of physics that you know. All the laws of physics that you know, you can straight ahead visualize them and apply here. For example, when Q is actually equal to rho, you know that when we are not in the relativistic regime, mass of the whole blob is not going to change. No matter how a blob moves, the mass of the blob is not going to change. Okay, we are assuming there's no mass transfer, we are assuming there's no boiling of that fluid or condensation of the fluid and so on and so forth. So mass of a blob in an isolated environment, in isolation, is not going to change. So I know that in the non-relativistic regime, this quantity is 0. To be exact, this quantity integrated over the instantaneous shape of the blob is 0. And now applying the Reynolds transport theorem, we get this means that this guy is 0. Okay. So this means that del rho by del t plus del dot rho u dv is 0. Now this is integrated over the instantaneous shape. Okay. For all arbitrary instantaneous shapes that a blob could take, for all of those arbitrary instantaneous shapes that a blob could take, we have the integral of this integrand 0. What does that mean? If a function's integral is 0 over all arbitrary domains, what does it mean? The function is 0 almost everywhere. But yeah, so this means del rho by del t plus del dot rho u is 0. Okay. And this is your mass equation or continuity equation as it is called. This is your continuity equation. So this integral form of the equation applies to the blob. Okay. Basically what it means is, let us say you imagine a fluid blob as it is deforming, moving through space. Okay. There is a control volume which is deforming with the blob. Okay, I am going to make the control volumes boundaries with a dashed line, and what I am saying is there is a control volume that is deforming with the blob, and if there is a shape or a volume that is deforming with the blob, you could either integrate it over the volume or the shape, doesn't matter, they are the same. Okay, but this distinction becomes important because you can actually derive a similar form of the equation for an arbitrarily deforming control volume. Okay, which you guys have probably learnt in your undergraduate first course in fluid mechanics, where you had the relative velocity term while defining the flux and so on and so forth. I don't know how it was formulated for you guys, but usually when I discuss that content in APL 106, I do it through the relative velocity in the flux. But where does that flux definition and all of that come from? It comes from when you integrate this term, this integrand, not over actually the blob of the fluid, but over an arbitrary volume. So this is a problem, first problem in your second practice sheet also. Imagine a separate volume. Okay. So imagine a separate volume which may be a subset of this BT, or it may even be outside this BT, some part of it. Okay. So let us call this as V naught and this is VT. Okay. The deformation of control volume is completely our choice. Okay. We pick a control volume that is deforming in a way which is making our algebra and making our life simpler. Okay. So that is our choice. So you can actually derive this version of Reynolds transport theorem for an arbitrarily deforming control volume as well. Okay. Give it a try in your first problem of second practice sheet, following the same procedure that we have done. You write it like this, instead of BT it is VT, then you write it like this, where this Jacobian is not the Jacobian of deformation of the actual fluid, it is the Jacobian of deformation of your control volume, and you carry on the procedure and you should be able to derive some equation, okay, which is for an arbitrarily deforming control volume. So this is your continuity equation or the mass equation. Okay. In the index notation, I can write this as del rho by del t plus divergence of rho u. So del by del xi rho u I equals 0. Okay. This is the index notation form of this equation. Of course, this holds in Cartesian coordinates. If you want to write this in cylindrical or spherical coordinates, you will need the divergence relation for that particular coordinate. You don't have to memorize it. You actually don't even have to write it in your formula sheets. That if it is required anywhere, that will be given to you. Okay. So you have del rho by del t plus del dot rho u equals 0. That is the continuity equation. Now we can get the same intuition that we got from del j by del t. So del j by del t was actually j times del dot u. What does this mean? This means that 1 by j del j by del t is actually del dot u. So the rate of change of volume per unit change in volume is actually equal to del dot u. Okay. Rate of change of volume per unit change in volume is del dot u. Okay. We can get a similar intuition back from this equation or from this equation by expanding this del dot rho u. So you have del rho by del t plus u dot del rho plus rho del dot u equals 0. What is this combination? The material derivative of density. So d rho by dt plus rho del dot u equals 0, which means 1 by rho d rho by dt is minus del dot u. So if del dot u is positive, then your fluid is expanding, the volume is increasing, and if the volume is increasing of the whole fluid, the mass of the whole fluid cannot change, the density is decreasing. Okay. So let us say you have an isolated blob of fluid that is contracting. For that, del dot u will be negative, d rho by dt will be positive, and vice versa. Now, as far as this course is concerned, we are always going to look at the flow that is characterized as an incompressible flow. Okay. Throughout this course, we are going to focus on incompressible flow except for the last 2-3 lectures if we get the time. So notice that I did not say incompressible fluid, I said incompressible flow. Okay. You may have a fluid which is very much compressible, for example air, but it as it happens that some of the flows you can model them as incompressible flows. Basically what it means is you can ignore any changes in density of the fluid while it is flowing. To be exact, the changes in density of the particles of the flow of the fluid you can ignore. Okay, d rho by dt is the change in density of the particle, it's a material derivative. So as the material particle is flowing down, the d rho by dt you can ignore. If you can ignore, then we term it as incompressible flow. So what we say is that d rho by dt, rather 1 by rho d rho by dt is approximately 0. Okay. So throughout this course what we are going to say is it's not approximately 0, it is exactly equal to 0 for us, and what we are going to say is that del dot u is 0. This is the continuity equation for my fluid flow for this course. That is, you have d rho by dt plus rho del dot u equal to 0. We are going to ignore this for a majority of this course and going to use this, that is del u1 by del x1 plus del u2 by del x2 plus del u3 by del x3 equals 0 in Cartesian coordinates and similar variants in cylindrical and spherical coordinates. Now similarly, if in the Reynolds transport theorem I use my q, which is the quantity, if I use momentum per unit volume, what is momentum per unit volume going to be? What is momentum of a blob per unit volume going to be? How do I denote it in the quantities that exist on the board? What is the momentum per unit volume going to be? So it's a vector. Okay. So if I denote q with this, then we know the physics law. So let me just make a star that these are the the axioms that we consider hold true. So the star is saying that d by dt of the mass is 0. So what is d by dt of this quantity? What is d by dt of this quantity? We know it from whatever you want to call it, Euler's first axiom or Newton's second law. What is this? This is d by dt of the total momentum of the fluid blob, which is nothing but the sum of external forces, which I am going to denote with this. Okay. So we have a d by dt integral bt rho u dv. Again, I can apply the Reynolds transport theorem and write this expression as b of t del by del t of rho u plus del dot rho u u, where this rho u u essentially is the tensor product of the two. Okay. I mean two vectors that are just juxtaposed to each other. So rho u u, so rho u tensor product u. So that is what we have for the momentum equation. Okay. That is what we have for the momentum equation. Now this is not really the final form of the momentum equation as it turns out. The idea is that when you have a blob of fluid that is deforming, okay, that is deforming, there are further distinctions in what kind of forces are being exerted that you can make. For example, if there is gravity, gravity is by virtue of mass of this blob. Okay. So if there was gravity, I could have written it as rho times g times dv integral. This would be the total gravitational force, right, on bt, integral over bt. Okay. So here this rho g, I am going to generalize this rho g as there is a f times dv. where this F is called a volumetric force. Okay, simply because this blob has some some volume in it. So, whatever infinitesimal volume you consider, that is going to experience some force. So, you add all the forces, and this F external you can write one component of F external you can write is going to be F times dV. Okay. Now, this is a blob. There is a surface of the blob as well. Okay, there is a surface of the blob, and the idea is that on the blob surface there could be some additional forces which may exist. These forces need not be normal to the surface. Okay, from solid mechanics, what do you know these forces are called? What are these forces called which act on the surface? Traction. This is a traction vector. It need not be perpendicular to the surface locally. It has some of its direction, but it is acting on the surface. It is not acting on the volume. So, how will I write that? I will write T dot, let us say, ds, where the integral is over the boundary of Bt. Okay, it is over the boundary of Bt. So, let me denote the boundary by St, let us say. Okay, so this is the traction vector. Now, we see that there are some simplifications that are possible in this equation. One is that I can take this F on the left hand side and I can start writing the combined integrand. I can start writing the combined integrand to be, we have del by del t of rho u plus del dot of rho u tensor product u minus F dv equals only if I could write this traction vector, the integral of traction vector, only if I could write as a volume integral, then I could combine that in the integrand and apply the same logic that we applied in the mass equation. Say that the integrand is 0, the integral is 0 for an arbitrary domain, so the integrand has to be 0. I can apply that logic once I convert this TDS to the form of volume integral. Okay. Now, to do that conversion to the volume integral, what we consider, let us consider a fluid element or a volume for that matter. Let us consider a tetrahedral volume. So, you have E1, E2, E3. So, you have a surface here, a surface here, and a surface here, and you have the slant surface. Okay. And let us apply our momentum equation to this kind of a tetrahedral fluid element, this kind of a tetrahedral fluid element in the limit of its volume going to 0. Okay. So, let us say it has a volume of delta V, we are going to apply this equation in the limit delta V going to 0. What do we get? Okay. In the limit of delta V going to 0, what do we get? We are going to see that. Okay. So, let us, so left hand side I can just write that as del by del t rho u plus everything dV integrated over delta V equals. So, this is an integral over the whole surface. So, you have this as the surface 1, you have a surface 2, you have a surface 3, and then we have a slant surface which I am going to call as n. Okay. So, this integration is simply going to be T n times S of n plus T 1 times S of 1 plus T 2 times S of 2 plus T 3 times S of 3. What I have done here is basically assume that this tetrahedral fluid element is so small that I can ignore any variation of the traction vector over the surface. Okay, I can just manage with the value at some location in on the surface and write it by multiplying it with the surface area. Okay, so this is what we get for the momentum equation applied to our tetrahedral volume. So this means in the limit delta v going to 0, my this integration is going to be 0, but I cannot necessarily say that the right hand side is 0. Okay. First of all, when is this integration going to be 0? This integration is going to be 0 because if you remember, there is a spatial derivative inside. So you have to be careful while saying that this integration is 0. You have to notice that this spatial derivative should not blow up, should not be tending to infinity at any part. In that case, you cannot say that this integration is going to be 0. You cannot integrate a very large quantity over a very small volume and say it is going to be 0. Okay. Large quantity times a small quantity might be a finite number. Okay. So we cannot just say that this integration is going to be 0 arbitrarily. We have to note that there is a derivative inside, and we are making a point that this derivative is not infinite. That is, this quantity rho u tensor u is a smooth quantity. Okay. This rho u tensor u is a smooth quantity inside the tetrahedral volume. Okay. This will be useful when we apply the same equation to an interface of two fluids. Okay. As you can think, when I apply this equation to an interface of the two fluids, the velocities might be continuous, but the density will not necessarily be continuous. So you have to be careful while applying this and saying that in the limit of delta v going to 0, this integration is 0. Yes, given that this quantity is continuous or smooth, differentiable. Okay. So assuming that holds, our integration in the limit delta v goes to 0 is actually equal to 0, and we are left with that T of n S n plus T of 1 S 1 plus T of 2 S 2 plus T of 3 S 3 is equal to 0. Now there is another interesting trick that I can do. Along with applying it to a small tetrahedral volume, I can apply the same equation to a disk, a very thin disk. Okay. Again, the disk has a volume delta V and let us say a surface area S, and I can apply the same equation to a very thin disk in the limit of delta V going to 0. Okay. And in that, what we will get is the same equation, that will be, so you have 1 on this side and minus 1 on the other side. Okay. What happened to the surface traction on this part, on the lateral surface? What happened to that? So in the limit delta v going to 0, I am making that disk infinitesimally thin. So what happened is that the area of that lateral surface is going to 0. That is how I am driving the volume to 0. I am saying that the area of this lateral surface is going to 0. In that limit, what you will get is, let us say you have a plus surface 1 plus and a 1 minus surface, you will get T plus S1 or S plus T minus times S equals 0. Okay. Basically what you will get is here that T plus is equal to minus of T minus. What it means is that if you have an arbitrary, let us say this is your fluid, you have an arbitrary surface, you consider an arbitrary surface, need not be a material surface, you consider an arbitrary surface and you want to look at traction vectors across the two faces of this surface. Then you can just directly write, given that this is a very thin surface, you can write that whatever traction vector is here, here it is the minus of that. Okay. Basically what we are trying to say is, so these kind of derivations you might have done earlier when we say that okay, we are looking at F equals ma of a very thin element. The mass of that thin element is going to be in the limit of delta v going to 0, the mass of that thin element is going to be 0. So, there cannot be any acceleration, finite acceleration of that thin mass element. So, the net forces have to balance. Okay. That is the same thing that we are doing here. The forces have to balance for very thin elements whose volume is negligible, hence whose mass is negligible. So, what this tells me is that if you look at T1 here, so here the surface 1 has a normal of minus E hat 1, the surface 2 has a normal of minus E hat 2 and the surface 3 has a normal of minus E hat 3. So, what this tells me is that minus of T1 times S1 minus of T2 times S2 minus of T3 times S3 equals Tn times Sn. Okay. So, now using this I can write this as, so I am going to write this minus of T1 as so let me write it as T bar of 1 okay times S1 plus T bar of 2 times S2 plus T bar of 3 times S3 equals Tn Sn. What are S1, S2, S3 in terms of Sn? What are, how can I write S1, S2, S3 in terms of Sn? I just replaced it with another variable. I said that minus of T1 is some T vector here. Okay, I just replaced it with another variable. We are going to see in a minute what are these variables. Okay. So, what are S1, S2, S3 in terms of Sn? So, S1 is basically Sn, let us say this is your n vector Sn times n hat dot E1, right, that is what S1 is. So, on for S2, S3 and so on for S2 and S3. So, what do we get here? We get T1 bar n hat dot E1 plus T2 bar n hat dot E2 plus T3 bar n hat dot E hat 3 is Tn. Okay, I have written S1, S2, S3 using this and I have cancelled Sn everywhere. What can you see this equation as? So, you have Tn written as this. First of all, how do I write this in index notation? Is there a simple way of writing this in index notation? How do I write this in index notation? So, n dot E1 is basically the component of n along E1, n dot E2 is component of n along E2, n dot E3 is component of n along E3. So, let me write that as Tn is T1 bar n1 plus T2 bar n2 plus T3 bar n3. I can write this very easily in index notation, right? I can write this easily in index notation as some t vector with a bar, let us say t bar vector I and I, or I can say it is some t bar vector j and j. The point here, the important point here is that the traction vector on an arbitrarily oriented surface, which is this n vector Tn, the traction vector on this surface n, you can write it as a linear combination of traction vectors, of some traction vectors, let us not bother about the physical significance of those traction vectors, times the components of normals of that surface. Okay. So, in short, I can write this traction vector, I can write the components of this traction vector as some T I j n j. I am going to replace this small t with a capital T. And now, for those of you who remember why we started all of this discussion, we will start to see why this is important. Okay. What was the motivation of all of this discussion? What did we want? In the momentum equation, what were we left with? We are left with a surface integral. We wanted to convert this surface integral into a volume integral. Okay. We are almost there. By using the Gauss divergence theorem, we are almost there. So, this integral of T ds over the surface I can write as integral over the surface. This is a tensor. So, in the vector notation you can write this as a tensor dot with n. So, this is basically T dot n ds, where n is the surface normal and we are integrating over the surface, and now from Gauss divergence we know this is going to be equal to from Gauss divergence we know that this T dot n ds is going to be del dot T dv. And now substituting this in our momentum equation that we had. So, substituting it here, we get integral over bt of del by del t of rho u plus del dot of rho u tensor product u minus f minus del dot t equals 0. And now we can apply the logic that the integration is 0 over an arbitrary shape. So, that means and this is just one step before, or rather two, let's say 2 lectures behind or 1 lecture behind Navier-Stokes equations. This is called the Navier's equation, where we are not modeling any of the properties of the fluid. Okay, we're not modeling any properties of the fluid, and as you will see in our next lecture, this part, this T, is where properties of the fluid begin to appear. Okay, remember where this T started acting from. This T started from this traction vector. If you have a blob of fluid surrounded by the same fluid, okay, if these boundaries are not actual material boundaries, but these are some arbitrarily controlled volume boundaries, okay, then basically what this traction vector is capturing is the force due to surrounding fluid on this blob of fluid. Force due to the surrounding fluid on the blob of fluid. So, those of you who know how friction, or let us say how intermolecular forces work, you know that this is going to be the interaction of this blob with the surrounding. And if both of them are of same fluid, different fluid, actually that does not matter, as long as both of them are some fluid and one is not vacuum, then you are going to have some interaction between the two, and that is what the molecular or the material properties of the fluid will determine. And so, this T tensor or this small t vector, the traction vector, will have those material properties in them. Okay. Rest all are kinematic and dynamic properties. Okay. So, this might seem like a very different way of looking at some equations which you may have derived, may not have derived. I do not know if in APL 106 you have seen the full Navier-Stokes equations and their derivation, but in a lot of textbooks you may see them presented in a different way. But it is important to know how this comes into the picture. Okay. And to get this Reynolds transport theorem, I had to go through all of that continuum kinematics. I could have easily said this is this Reynolds transport theorem, please accept it and moved on. Okay. But it is, I think, I feel it is important for you guys to see that this is not something that is just coming from the top. It can be derived, not with great difficulty actually. Okay. So, go through this derivation. I have uploaded the notes where you can see the derivation till Reynolds transport theorem. Okay, in a day or two, I'll upload the notes where we have all the governing equations and their discussion. Okay.